Well, hello, it's Rich Wurzbach, and I'm joining you for Grease Thief Thursday. And today I'm just going to continue with some work that I've been doing in the area of small motors, motor greasing. But instead of kind of, having the grease gun in hand and talk about that, I want to get down to the issue of having or just looking at how some of today's small motors are designed, and just ask that question about how does grease get in, how does grease get out, and so forth. So, relatively recently, we were asked to do a root cause failure analysis for a small electric motor, and this is just the end bell from that motor. And there was definitely a failure on this. The bearing catastrophically failed. And as a result, the shaft lost its centering from the bearing because of severe bearing damage. And you can see that the shaft in this case was rubbing on this penetration area. It actually transferred metal to the end bell in that case. And this is kind of what you would see from the outside. Now, this is a nice small one, so it's great for doing a little demonstration like this. And, but this could apply to larger motors and so forth. But what I can really show you here with this nice lightweight aluminum motor, which unfortunately died very young, is just to talk a little bit about grease flow. So when we have something like this, in this case, this is the drive end of the motor. You have your shaft penetration area here. The shaft diameter is going to be smaller than that, but the bearing is going to keep that centered. And then you've got this Zerk fitting here to add grease. And, the typical motor arrangement would be a single shielded bearing with the shield facing this direction towards me or towards where the windings are to protect against grease making its way into the windings. And then that leaves the open end of the bearing, because it's single shielded, leaves that open end of the bearing facing in this direction, like into the screen, if you will, or towards this end of the end bell. The nice thing about having this in front of us as we talk about it is I can turn this around and say, okay, the mystery of greasing, right? We've got a Zerk fitting, we hook up the grease gun, but where does the grease go? So let's find out. So I turn this around. You can see here's my Zerk fitting. It's in that position. And directly below that, you can see that in this aluminum casting of this end bell, you have a tube, okay, or a rounded section, if you will. And that rounded section continues kind of straight down from the Zerk fitting. And I can remove that Zerk fitting, and you can see that it's just a drilled hole there, and that has been threaded to take on this the Zerk fitting or a hydraulic fitting to bring the grease in. And then we can kind of trace the path, and you can see that the grease comes down through this tube where it enters the mounting area of the bearing. And what you see in here, let me see if I can point a little bit better, give you a little more detail for pointing here. But right here, you've got this cutout, okay? Now, this cutout would be facing the bearing. So your bearing would be mounted in here, and the open end of the bearing is up against this. So this cutout would then be introducing grease to the 12 o'clock position for this bearing. You can see the drill area. So this tube has been drilled. You can see where the drilling comes into the center of that square cutout. I think if I turn it on the side, you can see that, get a little sense of what we're seeing there. So this is your path of the grease. It starts here at the Zerk fitting, runs down through this drilled area, which you can see here is not a very large diameter opening. But, we're applying some pretty good pressure from our grease gun, and it's making its way down into this space and introducing it to the bearing. And it's often a question then of where does the grease go, okay? And if you can imagine this bearing mounted here with this tiny little cutout that just is, kind of the tip of my finger fits in there, we're not talking about a lot of grease between adding it here and going straight into the bearing. So when we begin to fill up that bearing, the question becomes, where does the grease go? So let's say it's packed, the bearing is packed at the very beginning, or when it's manufactured or sent out or what have you, and we're entering grease with the diameter of this hole, okay, and the distance it's here. We're not talking about a lot of grease, a couple of pumps to fill this tube, and then everything else is going into that bearing. Now we can calculate the volume that bearing can hold, but if it already has grease in it and there's no real pocket or reservoir here, what we're pumping in has to be displacing what's in that bearing. And then the question is, where does it go? Well, if we turn this back around and we have the top here, let's look at the bottom. Okay. Let's look here. I may have given it away, but this is, there's my Zerk fitting again. Here's the grease coming in. Here is the entry area. And then we have an exit area here. Okay. Another cutout. So to me, it appears to be part of the casting of this end bell, that it is casted with those square cutout areas for delivering the grease and then kind of gathering the excess so we give it a place to go. And then it has this casted tube that comes to the bottom, and this is where it gets interesting. I showed this to someone yesterday, and they said, oh, there's the hole. That is not the exit hole for the grease. That is just an area inside the housing. This is maybe a drip hole if moisture were to get into that or something. But right here is the location of that tube, and it has not been drilled. So now you look at this particular motor and you say, oh yeah, we provided a place for grease to go, but we haven't provided a way to get back out again. So what does that mean? It means that basically you're going to get this motor, it's going to have grease in it, you're going to relubricate one time, and now there is nowhere else for that grease to go. Where is the pressure going to build? Well, the only place that it could go is either come back out through this shaft, which is sealed, or push through the bearing and push against the shield, which is the only thing that's protecting it from getting to the windings. And just to talk a little bit about how grease moves. So grease has a consistency. It's a function of the thickener. And when grease is static, that thickener kind of holds that in place. When grease becomes dynamic, it's easier for it to flow. And so this really translates into, where does the pressure get applied? Where is the grease going to flow? And I said about it could be through the shaft here, and that's possible because you do have some rotation there, and it could be thinning the grease, but we do have a seal there, right? We don't really expect to pump grease and have it coming out that seal. So that seal is usually pretty effective at keeping dirt out of the bearing area and keeping grease in. So it's got nowhere to go. And I'll argue that on a motor like this, after the very first time you grease it, there's nowhere for that grease to go. And that's just part of the design here. So while that could be kind of eye-opening, I don't know that in retrospect was responsible for the failure of this particular bearing. We had some other issues going on, but certainly it's something that we think about. You can see that this particular bearing has some pretty significant overheating going on. There's a lot of damage to this inner bearing raceway. And there's also, when you look at the individual balls here, I guess you can tell that it's not spherical and shiny. This is really beaten up. There's been some skidding. There's some flat marks on here, and some material has gotten into this as well. And as I look back on this particular example, I know, and you can see the pretty severe damage here from the cage. And they've really been bent around pretty severely here. A lot of wear, a lot of transfer of metal. But we did also have an additional issue here where there was an installed aegis ring. And an aegis ring is designed to give grounding to the rotor and allow that any kind of voltage to go to ground. And this is important where we have the installation of VFDs and maybe not the proper insulation class for the motor as designed. It might be a VFD retrofit, or maybe we're just buying these types of motors. But definitely some issues here. Those aegis rings did fall off. We saw that, and that could have been the initiating event for this. But as we look back on it, it's like there's other things to consider. And I think that each time we do a root cause failure analysis, we want to be thinking about how, not just what is one thing that caused the failure, or even like the one most significant thing. If there's 2 contributors and 3 contributors, we want to ferret them out. We want to get them out and have them as contributing causes as well, because it's going to allow us to address things, and really not only in just this motor, but in other similar motors, or if the issues that we discover are practice related, like poor lubrication practices or dirty greases, they extend beyond this one investigation. So we do want to try to find as many things as we can to really benefit from the cost and the time that it takes to do an experiment like this. So yeah, foreign material, jamming this up, the balls are skidding on the raceway, flattening it out, generating a tremendous amount of heat as well. When that happens, as they get jammed up, because you get that direct rolling, and it's kind of amazing that you've got the outer race, which doesn't look bad here at all, still quite shiny, but the inner race just looks absolutely terrible. And so we also look for things like, is it sliding on the shaft and so forth. But my main purpose today is just to share what we saw here on this one with respect to the housing. And, when we teach training classes, that's one of the things when you talk about grease lubrication is, ask that question: where does the grease go? How much grease am I adding, and where do I expect it to go? And today we give you a little bit of insight into just how little space there is in, only a couple of pumps worth. And once that's filled, and if it has nowhere to go, it's headed to the windings. And that's not good for anybody involved. So, what do you do about something like this? Well, first, it's an awareness. Are you buying motors that are essentially throwaway motors? And these are, let's be honest. This pretty much 10 horsepower and down is considered a throwaway. When we say throwaway, is it worth getting maintenance done? Is it worth getting them rebuilt, and so on? And if it's not, these lower horsepowers get thrown into this category of where we're not even designing them for reliability. This is not designed for reliability. This is designed for cost. It's cheaper just to drill one hole and not drill the other, right? Now, you can make the argument, why wasn't this a sealed bearing? Why does it even have a Zerk fitting on this at all? And I'll argue that if it truly is a throwaway bearing, don't put a Zerk fitting on it. Don't try to add grease. Don't fool yourself into thinking you're doing any good whatsoever of pumping grease into this bearing, because it has nowhere to go. So instead, let's talk about, sealing everything up and truly making it a throwaway. Have some sort of monitoring for that. But here's what happens. You make that kind of general decision on what we do with certain size, certain horsepower, and so forth. But this particular motor was in an absolutely critical system in a biomedical application. So size does not necessarily relate to criticality. The 7.5 horsepower motor is critical in this application. And if it is, and you're buying motors that are generally treated as throwaway, low reliability requirement applications, better make sure that you're getting a version of that motor that is designed for lubrication, is designed for reliability, is designed for the application you have. This particular motor was not. It was in a critical application. It didn't last long. So that's all I wanted to share with you today. Kind of show you what we have found in doing root cause analysis, looking at failed components, looking at the grease that comes out of these failed components, being able to analyze that. And thankfully today we have a lot of tools for that. We have the grease thief sampling tool that allows us to take a representative sample of grease and perform a number of different tests with that small sample of grease. That gives us insight into where contaminants, oxidation of the grease, as well as the changes in consistency. We have that as an option. We also have the option to do a more detailed root cause analysis. And when we're asked to help a company out with that, we're not just saying, okay, yeah, the bearing was damaged. You have a damaged bearing. It's not enough. You have to go beyond that and say, what's the order of events? What kicks this all off? What is at the root cause that led to this failure? And what else can we see when we're here? So we're going to take something like this and tell that customer, do you realize that you have a Zerk fitting on here, but there's nowhere for that grease to go? It is built in lack of a reliability. It's built, you could make the argument it's built to fail. And some of the folks from this company, raise that question. Was it designed to fail? Is this a money-making thing? It probably isn't deliberate as we might think. It's probably just falling through the cracks in that we have, a run to failure kind of approach. We have a throwaway motor for 90% of the applications for it. But it's important for us to recognize when we need to, when we have an application where that reliability is very important. So thanks for your time today. Wanted to share just kind of a quick tip today on Grease Thief Thursday. We'll do this again next month. And we're always looking for your recommendations and ideas for what you would like us to tackle next, whether that's things like disruption to the supply chain, whether it's how do I deal with unavailable greases, how do I check compatibility, how do I sample a certain kind of machine that I have, and how do I change my maintenance strategy from one of greasing and kind of hoping things don't fail to monitoring, evaluating, looking at the failures that take place and taking actions to improve and achieve a state of precision lubrication to get maximum reliability from my components. So thank you for your time and have a good time until we see you next time for Grease Thief Thursday.